My name is Ishul Abdul Halin, and welcome to my video on the introduction to the 68K microprocessor. This video is the third part from a 6-part series that aims to give you introductory knowledge about this topic. Hopefully at the end of the series, you would have gained an understanding on what the 68K microprocessor is, how it works and how it is programmed. Now, for you to better understand how the overflow flag changes state, it is best to do a little revision on sign numbers. A sign number is a method to present both positive and negative binary numbers. The magnitude of a sign number is encoded in its most significant bit, MSB. When the MSB of a binary string is 1, the string represents a negative number. In contrast, when the MSB is 0, the binary string represents a positive number. Let's look at an example that shows an 8-bit binary string. The number is 00000100. We will now assume that this number is a binary sign number. Notice that the MSB is 0, thus, this number is a positive number whose decimal equivalent is 4. In order to write -4, we would use 2's complement. Initially we will invert all of the bits representing +4, resulting in the following binary string. 1 is added to the least significant bit to obtain -4 in binary. We must also understand the range of numbers that can be presented using sign numbers. The range is from -2 to the power of n, up to 2 to the power of n, -1. N is the number of bits used in a particular binary string. Let me show you a quick example of what I mean. Consider an 8-bit signed number. When all bits are 0, the equivalent decimal representation is 0, when the MSB is 0 while all of the lower bits are 1, it is equal to 127 in decimal. In contrast, when the MSB is 1, and all lower bits are 0, the binary string is equal to -128. Finally, when all 8 bits are 1, the decimal equivalent is -1. Thus, the range of values that an 8-bit sign number can represent is from -128 to 127. This result confirms the sign number equation range stated here. Take note that any other number, outside of this range, cannot be represented by an 8-bit sign number. For example, -129 or 128 cannot be represented using the 8-bit sign number format because it simply lies out of the range -127 to 128. In other words, -129 and 128's value is said to be in an overflow state if it were to be represented using an 8-bit signed number format. This statement is very important in relations to how the overflow flag in your microprocessor changes state. Now, let's read the statement about how the overflow flag changes state. The overflow flag is set to logic 1 when the result of an arithmetic operation performed on sign numbers results in a value that is out of the 2 to the power of n, up to 2 to the power of n, -1 range. Otherwise it is reset to 0. Just for fun, the range for an 8-bit sign number is from -128 to 127. The range for an 16-bit sign number is from -65,536 to 65,535, and the range is from -4,294,967,296 to 4,294,967,295 for a 32-bit sign number. Any number that results from an arithmetic operation that is out of this range, will cause the overflow flag to be set. Note that to analyze the overflow flag status, you must treat any given binary string as a signed number. This is very important. It's time for an example. The first example concerns the addition of two signed positive numbers, that results in a signed negative number. Let's have a look. Consider the two 8-bit signed numbers presented here. Notice that the MSB of both binary string is 0. This means that both numbers are positive numbers. Now, let's add them up starting with the least significant bit. Bit 0. 0 plus 0 equals 0, a 0 is carried to bit 1, and now we have 0 plus 0 plus 0 equals 0 in bit 1's position, a 0 is carried to bit 2, and 0 plus 1 results in a 0 in this position with a 1 carried to bit 3. We now have 1 plus 0 plus 1 equals 0 with a 1 carried to bit 4, in bit 4th position, we now have 1 plus 0 plus 1 equals 0 with a 1 carried to bit 5. At the 5th bit position, we have 1 plus 1 equals 1 with a 1 carried out to bit 6. The similar operand in bit 6 results in a 1 and a carry of 1 into the MSB, bit 7. Finally, we have 1 plus 0 which results in 1 as the MSB. Since the MSB is 1, the result is a negative number. Now let's look at the decimal equivalent of the two signed numbers that we added earlier. The top 8-bit string equals 100, while the bottom string equals 124. Addition results in 224. Although the addition is correct, the result falls out of the range that can be presented by an 8-bit signed number. Moreover, the resulting binary addition value is -32, which is incorrect. Due to the results, the overflow flag is set to 1, signaling that an overflow has occurred. How about another example? Okay. We are now going to add two negative 8-bit numbers together. If the result is positive, then we know that the overflow flag will be set. Let's have a look at the two 8-bit signs number presented below. The MSB are both 1, signaling that these two strings are representing two negative signed numbers. Adding them up starting from the LSB results in the following string. The results MSB is 0. We are ignoring the 1 carried out of bit 7 simply because in the microprocessor the addition of 8-bit numbers have to result in an 8-bit number, thus, we have a positive number. Now let's look at the decimal equivalent of these binary string. The top 8-bit string equals -92 and the bottom string equals -68. The addition process yields -160 and again, it is out of range. Let's take the decimal equivalent of the results. It is 96 and is incorrect, since the binary result is incorrect, and that the decimal result is out of range, the overflow flag is set to 1. As a conclusion, you will know that the overflow flag is set to 1 if you do binary addition and obtain wrong binary results, or if you take the decimal equivalent of the two numbers, do the arithmetic operation, and obtain a result that is out of range. It is up to you which method to use. Personally, I prefer to take the decimal equivalent of the signed numbers presented to me, and check whether the result is in or out of range, then I would determine the status of the overflow flag. It is much easier to do it this way, but for practice, I would suggest you to do it both ways. Note that the overflow flag is also affected by the subtract operation in a similar manner as well. Now it is your turn to determine the status of the overflow flag. Pause the video and try these questions and see if you get the correct results. Okay, did you get these answers? Yes. Very good. Let us now study how the carry flag in the status register changes state. We have seen in part 2 of this video series that the carry flag is an indicator for the occurrence of an arithmetic carry or borrow when an arithmetic addition or subtraction operation is carried out. We should also know that a carry is generated when the MSB results of an unsigned arithmetic operation is shifted out of, or, into the binary format representation. An example will clarify this. We now are presented with two decimal numbers, 254, and 4. Adding them up will result in 258. The hexadecimal equivalent is FE plus 4. The result is 102 in hexadecimal. Let's do the 8-bit binary addition of these two numbers. Note that we will treat these numbers as unsigned numbers. This is because we are analyzing the C flag. Starting from the LSB, we have 0 plus 0 equals 0, with a 0 carried to bit 1. Now, at bit 1 position, we have 0 plus 1 plus 0 equals 1 and a 0 carried to bit 2. Now, we will do 0 plus 1 plus 1 at bit 2 resulting in a 0 with a carry of 1 to bit 3. From this point on, all operands to be added is 1 plus 1 which results in 0 with a 1 carry to the next significant bit. Note that at the 7th position, the addition causes a 1 to be carried out of the MSB. This 1 causes the carry flag to be set to 1. If you look at the 8-bit binary addition results, its decimal equivalent is only 2, which is clearly wrong. The answer should be 258. You can obtain 258 if you treat the C flag as the MSB. Surely this is something to think about. Here we will do one last example to analyze the status of the carry flag. We will be using a 4-bit unsigned number in this example for simplicity. The two 4-bit unsigned numbers to be subtracted are 8 and 7. The result is 1. The 4-bit binary equivalent is shown. We will start subtracting these two binary numbers from the LSB. As usual, at bit 0 we have 0 minus 1 which cannot be done. We need to borrow from bit 1. However, bit 1 is also 0, thus we will borrow from bit 2. Again, bit 2 is 0, we now borrow from bit 3. This causes bit 3 to be 0 and bit 2 to be 2. Bit 1 can now borrow from bit 2, causing bit 2 to be 1 and bit 1 to be 2. Bit 0 can borrow from bit 1, turning bit 1's value to 1 and bit 0 is now 2. Now, subtraction can be done easily. We will cross out the first operand, to avoid confusion. With the new operand at hand, we perform the subtraction starting at bit 0. 2 minus 1 equals 1. At bit 1 position, we have 1 minus 1 equals 0. At the next higher bit position, we again have 1 minus 1 equals 0. Finally, at the third bit position, we have 0 minus 0 equals 0. Note that in order to perform this subtraction, the MSB, which is bit 3, did not have to borrow, thus the carry flag is reset to 0. This indicates that a borrow into the MSB did not occur. Moreover, the binary results is also correct. We have arrived at our final slide. As a conclusion, to analyze the overflow flag status, you must treat your given operands as signed binary numbers. You must check whether the arithmetic operation result is in range of the signed number representation to determine the status of the overflow flag. For the case of the carry flag, just treat your operands as unsigned binary numbers, and check whether a logic 1 had to be shifted out of the MSB or not for an addition operation. Or, check whether the MSB of the first operand had to borrow in order to perform a subtraction. Answering this question correctly will give you the status of the carry flag. That's all we have for you in this video. Thank you for your time and attention. Have a productive day.